So a floor system of an office consists of a grid of beam supported by column as shown in the figure number 4.4. So there is an office building and it has a beams. As you can see, these are columns at these corners. These are columns. As you can see, these are the columns. This is, by the way, the plan view. So these are the columns at those corners, and these are the beams. These are the beams, and they call it panels, or you can say that this is a slab. So that is the slabs that you can see. There are different kind of a slabs, so you can see what is different kind of slab, meaning that you have this panel 1 on here. If you want to read it, sometimes they put this A, B, C, D, and they put 1, 2, and 3. So if I want to read this panel number 1, I would say that D1, A1, and then C2 and D2. So that's how you can read it, like a D1 for this corner. For this corner, you can say A1, and then you will have this C2, and then you will have this D2 and D2. That's how you can read the panel number 1. Okay, and similarly you can make it panel number 2, A1, B1, B2, and A2. So that is just a designation. So in case someone wants to put the put some designations which one to read, then you can read through. So I hope you understand the columns and beams, and where is the slab. Slabs are in the in the middle sections. There is a slab, and those are the beams. And the beam dimensions is given, like 7 millimeters depth and 500 millimeter wide, and column is 500 by 500. An allowance of 0.5 kilopascals to be made for partition that are to be deflection sensitive, that are not deflection sensitive. So we have a additional dead load 0.5 kilopascals given to us. That is for partitions. Imposed live load is given 3 kilopascals for office buildings. When you have AS1170.1, for that office buildings, we have 3 kilopascals. It's basically saying that 1 meter square by 1 meter square, you have that many persons are sitting in the office building. We have short-term factors 0.7, long-term factor 0.4, basically saying that for short terms, when the office building open, you will not have all the users coming on the first day of opening of the building, so you are reducing that one. Long term also, during the long terms, you will not have all these live load coming on the same times throughout the life of the building. So there are short term factors and long term factors relaxing those factors. We will see where we can see. And by the way, these are also taken from the 1170.1. Let me show you, just give me a minute. I will open the standards for you, in case if someone wants to interested that one, and that is in these standards, I think. Yeah. So let me show you that in the standards. So you remember this in SD2 we have 1170.0. In these standards we have these short-term factors and long-term factors. In table 4.1, we are in the office building, so we have 0.7 and 0.4. That is given here, table 4, but it's given in our examples. But in case in the couple of months you are going to be graduate sitting in the one of the design office, and you are designing some of the slabs, so in that case you might need to refer this one. For office buildings, I think we have these 3 kilopascals given, so you can again refer AS and ZS 1170.1 in case the live load is not given. Then in that case you can have these 3 kilopascals typically used in the office general use 3 kilopascals given here. So that is just a quick reference where those values are coming from. To satisfy fire and durability requirement, take the FC-32 megapascals. If you remember that we have this durability and fire resistance in week number 2, I believe, where we have taken some examples how we can select different concrete compressive strength. And clear cover is given 25 millimeters. limit to total deflection is 1/360. So they already given to you in case if you wants to take the reference for that. So there is a tables that it can going to show you that tables in our AS3600 2018. This in this standards in table 2.3.2 you have a some different members, all members, total deflection. It's given span over 250, over 800, 1/50. You read about it, this one, and that is a different deflection limits given in these tables in case you want to have a reference. But in our example, it has already given to us is a length over 360. That is given here. We need to use class and reinforcement. Typically in the slab we use N12 bars. Why we use N12 bar? Because these slabs are very sensitive to the crack due to shrinkage and creep, and they are thin and wide, widely spreaded. So for that case we need the small bar but closely places small bar. So therefore we generally use N12 bar, unlike in the beam we use N16, N20, N24 and so on. So we use N12 bars. Determining the slab depth, which is to be uniform, yes, throughout. So we just need to use the uniform slabs. Design the reinforcement in the corner slabs. I will show you how to design in the corner slab. And determining the total floor load on the beam AB and beam AC. So we need to find what is the load coming on the AB and what is the load coming on AC when you design the slab. EC value 30,100 given to us. In case if you want to take a reference for that one, in case then you go back to that week table number 3.1.2. we have 32 megapascals given, so EC value is 30,100 megapascals. So that is taken from table 3.1.2 in case if you want to take a reference for you. So that is the reference table 3. But it's given in our example, so but I'm just pointing it out. Density of the concrete is given 25 kilonewton per meter. It is already given, but in case some students need the refreshment, so we can go to the AS/NZS 1170.1 permanent impose and other actions. If you remember, there was a table here, the unit load of material and constructions, table A1. In that one you have a concrete dense aggregate unreinforced, you have 24. You need to add 0.6 for 1% of the steel reinforcement, so 24.6 rounding off to 25, because 24 comes when your concrete is unreinforced. When you put the steel in, you need to put the 0.6 for 1%. If you're 2%, then you take it 0.6 plus 0.6, 1.2. So we just rounding off to 25 kilonewton per meter cube. That's the density of the reinforced concrete, and that is coming from here in appendix A of 1170.1 2002. That is just for your reference and for your knowledge where those values are coming from. And shrinkage strain is given to us 700 times 10 to the power 6. These figures I already explained. Immediately when I look at these figures, so there is a very quick note for two-way slabs. Unlike in the one-way slabs, if you remember there was a one-way slab. So if you remember there was a one-way slab, I always going to take a reference from the one-way slab. Now one-way slab like it is supported on two edges. Generally, this is typically this one-way slab was supported on these ones. And in these one-way slabs, we generally have this is LX, like shorter span. That's how the design we do it. Like we don't do it in the other way because there was no bending. So this will bend just like this, right? It will just going to bend in that fashion, just bend on that fashion. So we generally design only for one-way side. And that is the short span. So we provide these main reinforcement along this one, and then temperature shrinkage reinforcement we provide along the longer span. So this is the typicals, LX over LY. Generally speaking, in here when you have this is let's say 5 meters, then you will have let's say more than 5 meters along this way. So it would be LY. So LY is a longer span, let's say 15 meters. So Ly on Lx is equal to 15 on 5, you have 3. Typically this is the case like in the one-way slab. This is one-way slab. This is one-way slab where your edge is supported by two side only, and you have a one side of bending, right? You have only one side of the bending. You don't have bending on this side because this edge is supported. You don't have bending going on these sides, right? So that is dominated by one side only. So we just calculate about Lx. We just get the bending moment, positive bending moment, mx star, negative bending moment. Here we provide bottom reinforcement, top reinforcement, and so on. But in two-way slabs, what happens typically that this length is reduced, your span, and generally it sits in Ly on Lx less than or equal to 2. In that case, typically in that case, if your length, so my intentions here that your Ly is the notation is like that. Ly is a longer span and Lx is a short span. That's how you put the notations. Let me turn off my camera. I appreciate that. So in that case, what you can do it, you go on the standards at the front, and somewhere they will write about that one, somewhere alphabetical orders, as you know, length, Lx and Ly. Lx, shortest effective span of the slab supported by 4 is very mouthfuls, very good information that your Lx would be shorter effective span and Ly is a longer effective span. So you don't need to remember that. It is clearly mentioned here for two-way slab that if you have someone put your slab in front of you and saying that it's supported by 4 edge, and can you please let's say we have a 5.5 by 7.5, so you have a 5 meter by 7.5 meters here. So someone said that can you please tell me what is your Lx and what is your Ly? How do you note that one? So you can come back. You said no, I don't want to remember. That's fine. Lx is a shorter effective span. Okay, so Lx is your shorter effective span, and then short side here is 5.5 meters. It is not effective. You know, the effective has some definition, and the longer span is 7.5 meters. So that's how you put the notations that here this is Lx and this is Ly. I hope the students would not have any difficulty to put the notation Lx and Ly. Basically in the two-way slab, in the one-way slab, the Ly does not come into the pictures because we're just designing it along the Lx only, right? Because it's supported to and it's just bending on this one. But here in the two-way slabs, it bends like this along this side, and it will bend this side as well, right? So that's the notation. And generally speaking, this ratio Ly on Lx, typically that will be less than 2. And that is, again, you no need to remember. Some of these tables will give us the signal. Some of the tables giving the signals, meaning look, this is slab system multiply K4 rectangular slab supported on 4 sides, Ly on Lx 1, 1.25, 1.52. They don't provide more than 2, because then if it's more than 2, then you typically going for a one-way slab. They did not mention anywhere, but just this is a typical behavior here as well. If you look at these tables, you have greater than 2, then you have a constant value. That's constant value is given here, but that is the two-way slabs that typically I read from that standard. So that's how that's typical behavior, meaning that your slab, let's say you have the slab, I think they are more like what we call more kind of square, rather than just so more kind of a square kind of a slab, that is two-way slab. So you're under this loading, when the beam is dead load and live load, they will bend like this, and they will bend like this as well. So this is the point where you have same deflections, right? So I hope you understand that. Probably I will have a paper somewhere. Let me get that paper for you, and I will explain that one. So in here, if I open that one, this is the papers, and then in the one-way slabs you might have only this kind of bending. In two-way slabs you will have bending like this, bend like this. So everything, all four corners will be lifted, and they will bend like this, and the middle point have the same deflection. You have bending on here and bending on here. That will happen when your ly by lx ratio typically between 1 and 2, so that will have these bendings. If you have this edge is very long, ly let's say very long, then you have just these things happens, right? So that's only one way slab. So that is a typical thing set. All right, so let's start doing it. Now you remember that the first one that we might need to assume. Look, the when you have a two-way slab and one-way slabs, the two-way slabs are stiffer, is stronger, and therefore you need the thinner slab. So generally in the practice, engineers prefer two-way slabs. So two-way slabs can be thinner, like if you use one-way slabs, it would have a thickness. If you remember that last time we have some thick slabs that we use, but in the two-way slab, typically this is general rule of thumb. It's not, don't say that okay this is always the case. No, this is not always the case. Sometimes in the two-way slab you might need to use the thicker slab depending on your loading and critical panels that you are designing. But overall general rule of thumb saying that okay, two-way slabs could be stiffer and more thinner than the one-way slabs. Okay, so now you remember that our depth of the slab, that is the first depth that we need to do, is a trial depth. We just need to try the depth and satisfy the some of the conditions. Particularly for the trial depths, we need to satisfy the serviceability conditions, because these slabs are not governed by the bending. Like you remember that beam that we have it, that we generally do the bending capacity, like can you please tell me 5 mu, and then we check it m star, and then you said okay, the section, the reinforcement, everything is okay. But here in the slab, they are not sensitive to the strength. They are sensitive to the, they are not sensitive to the strength. Of course, we're going to make a check for the strength, but they are mostly governed first by the serviceability. They will deflect too much. So that deflect too much, that means we need to control it, making sure that your slab will not deflect. So someone might say, okay, can I use 10 millimeters? Can I use 20 millimeter slab? No, it's too thin. It's practically not possible to use these 10 millimeter and 20. Where is the cover? Where would we put your Rio? It is you can't have just slab like this, 10 millimeter slab, and this is very unpractical slab that you are talking about, right? So someone what is the my numbers? Yeah, so not 10, 20. Generally, typically you might have a 150 millimeter or 120 millimeter, 200 millimeter. That is a typical thickness of the slab that you're going to come up. Now you might say, okay, I don't want to remember that one. So in that case, these tables might help. These tables are not, this table is not magic. They will not give you the answers, but they will at least give you the number that you can start with. These tables generally use everywhere because these are non-dimensional tables. If you are in UK, USA, Australia, these tables are typical. All around the world, if you are in Asian countries, still they use it. India, China, everywhere they use. These tables are typical. Those factors are there. They are typical because it's non-dimensionals, right? So in that case, how do you read it? 4 edge continuous, 1 short edge discontinuous, 1 long edge, 2 edge discontinuous. There are 4 different cases are given to you. That's how you read it. You can find ly on lx. For our case, we can find it out. Ly on lx. Generally, we need to use these lnx. Okay, the lnx meaning that clear spacing. lnx meaning clear spacing, meaning that if you have a slab here and this slab is sitting on the beam, then this is ln, the clear spacing. This is ln. Now someone might say, okay, you know that, but how do I know? Yes, that is a good one, that you can just come back here and somewhere read it. ln, length of the clear span in the direction in which moment are being determined. So that is the written here, ln clear span. So that's clear span, meaning that you have this center to center distance 550 and the beam width is 500. So in that case, you have center to center distance 550 millimeters, and then you have this 250 here because this total is 500. Total is 500, and then you have 250 millimeter. So in that case, you have this ln equal to 5500 millimeter, take away 250 here, take away 250 millimeter, take away 250 millimeter from here. So you get about 5000 millimeters as a lnx. So lnx is equal to, I found lnx is equal to 5000 millimeters. Similarly, you can also find lny. Lny is 7500. Again, you can just use the same notation here. Instead of 5000, you can put 7500. So you have 7000 millimeters. Now, but here we just need to control by lnx. So the good thing is you have these control by lnx that you need to control it. Now, if someone might say, okay, how about you find ly on lx? So ly on lx, I think I can show you the definitions. Ly on lx. What is the definition of ly lx? Did they give you? Let's put it here. Ly, longer effective span of the slab supported on 4 edge, and the shorter effective span. And what is effective span, by the way? L effective. So if you can find L effective effective span of the member taken as smaller of ln plus d and ln, and we don't know d at the moment, so we can't just calculate the effective span. So as I mentioned, this is too much conservative. It's not that one. So someone say, why you not using L effective? We don't know therefore we just take it ln effective equal to L, which is this one. So just a conservative, just to start with, 7000 over 5000, you will get 1.4 about. Okay, so that's good estimation, not too much worry about. So ly on lx is about 1.4. Now we have in that case, let me find it out what we are doing it. Just give me a moment. I keep my solution handy as well. Okay. So in that case, we have about 29. You can take it ln over 28. Now someone might say, okay, what would be your critical panel? Critical panels mean these corner panels will be criticals. Your design will be governed by these panels. These are the critical panels. These are the corners. One would be critical panels where your two edges are discontinuous. These are the critical panels on these sides, right? This one would not be critical panels considered, because you can see these two edges are discontinuous here. So this beam will have a more deflections. You can see if it is uniform loading, this will be more stronger. So your design will be governed by those one where your two edges are discontinuous. So two adjacent edge are discontinuous. That's good, because this would be your critical panels. That's we going to take it. So let's say take this one. We have 1.4, and we don't know superimpose qg equal to qq is 6 kilonewtons. Maybe take it 6 kilonewtons, because we already have 3 kilonewtons. 3 kilopascals is already live load, so it's more than 2 kilopascals. So we will have in that range. So let's take it in between, which is ln x over 29. So ln x over 29 equal to ds, which is depth of the slab. It's just a starting point. Okay, and then if I just wants to calculate the depth of the, by the way, depth of the slab is this, is ds overall length. Someone might say, okay, again you put the new number for me. Can you tell me whether it's coming on that one or not? ds overall depth of the slab or drop panel. So that sounds good. So we have this ds. So if I want to calculate that, ln x is a 5000. So you put 5000 millimeters over 29. So 5000 over 29. Let me do it on my calculators. Where I put the calculators? Oh, here you go. So you have 5000 divided by 29. You get about 172 millimeters. Look, your builders will not going to like it if you put 172. So generally we will put the rounding numbers, just lower it down, not increase, not put 180, just put 170 millimeters. So that is the good starting points. Let's try let's try ds equal to 1. Let's look, example has not started yet. We need to start somewhere. And look, these slab examples, you don't need, like all this design, you don't need to blindly follow the numbers. Blindly follow the numbers meaning when you get the numbers by the calculators, you need to feel it. You need to feel it meaning that 170 millimeters numbers is making sense in the real world. Does it really happens? Because sometimes in the calculators, if you just accidentally press only 500 divide by 29 and you might end up with 70.2. Well, that's okay. Let's take 70.2. No, you just stop there and have a feeling whether those numbers are making sense or not. You see what I mean? Everyone can have some accidentally put some numbers in the calculator and you end up with some numbers that does not make sense. So always stop, think, and feel it whether those numbers making sense or not. Okay, and I will tell you that 170 millimeters looks reasonable. That is not an big issue. Like 120 to 240 in that range, it would be good. So that is 170. Let's try with that one. Why we need to try this one? Like these examples where you have FD effective, thus we need to integrate the Z. Otherwise we don't need to try that one. Okay, I supposed to write that close first, right? Let me write this close here. That close 9.4.41. And by the way, they written here that you have one-way slab and two-way slabs deemed to comply ratio. So let me write that one. Close 9.4.4.1, and that is for two-way slab, and that is to do with L effective over D less than or equal to K3 K4 delta LEF divide bracket 1000 EC on FD effective over 1/3. Okay, now here these equations will going to give you D minimum. These equations will give you D minimum. Now someone might say, what is D minimum? D minimum is basically when you have a slab, you have a reinforcement. Let's say you have a reinforcement here. Now D minimum meaning that from this reinforcement to the top of the slab you have this D minimum. That is the D, at least you need this D. You can't go lower than that one. So that is the D minimum considering the criteria. Considering criteria meaning that if you use your depth of that slab more than the minimum, your slab will be comply with the standard deflections criteria, that your slab will not deflect too much. So that is to give you the D minimum. Now here one catch, L effective is easy peasy. Watch, if someone wants to calculate L effective, you can calculate that L effective simply by doing this. Like if you go back here, and L effective span of the members taken as minimum of Ln plus D and L. So they say that if you want to calculate this one, minimum Ln plus D or L. So minimum Ln, let's say 5000, because if you remember that we calculated Ln, we calculated Ln 5000. You remember that we calculated Ln clear span, clear span for X directions, and depth of the slab is 170. So you can put depth of the slab 170. What is L? L is written here. That is a center to center distance between support of the flexure member. So is a center to center distance, meaning that we already given the center to center distance is this 5500. So let's put that one. So or 5500. So you have this minimum of 5170 or 5500. You have effective 5170. That's how you calculate the effective. If you want to calculate on the L effective X, if you want to calculate on the other directions, again you can put here X, minimum of L and Y, D is same, and you put Ly, and here you have Lx. So minimum of you have 7000 plus 170, Ly was 7500, so you have minimum of 7170 7500, you have 7170 minimum L effective Y, right? So that is the that is the that is how you calculate the effective span. So if someone asks you, can you calculate the effective spans, you should not have any issue to calculate effective span. In our examples, they generally have triggers with the delta over L0. So we just need to convert it into the L0 formats, right? For L0, I think there is a quite a simple definitions for L0 as well. So let's say if I want to calculate L0, so I hope you understand Ln, which is the clear span. So if you have a slab, this is your Ln. Center to center distance is L. L effective equal to, this is, let's say, D, minimum of Ln plus D or L. Okay, so I hope you understand D, I hope you understand L effective, I hope you understand Ln, I hope you understand L. Now one new terminology comes L0. So if you want to come across L0, probably written here, L0, L minus 0.7 times sum of value of A support and span. So that's easy here. L0 equal to L minus 0.7 A support and minus 0.7 A supports. Where is coming from? I think that is coming from here in this clause. And what is A supports? I think there is in the clause number 6. I think we discussed that one in the last class, but I can show it to you again here. I think in the section 6 somewhere they talk about this L effective and all. Let me find it. Here you go, L effective sum of this n span, also figure number 6.1.4b. So let's find that figures. 6.1.4b. Here you go, A support is just from your point of the supports to the centers. Okay, so it's just like a 250 in that range. So A support is basically this distance, like if I take this beam and let's say this is the beam, you have 500 millimeter beam, then A support will be just 250 millimeters, just divide by 2. All right, so if I want to calculate L0, we can calculate that one easily, that L0 equal to, because it's a both side 0.7 and 0.7, L, I think we know L was center to center distance 5500.7. A support is 250, is just half of your beam width, and this 5500 take away 0.7 times 250, take away 0.7 times 250, you get 5150 millimeters. So instead of L effective, we're going to use this L0 value. Right, so that's all good now because they just give you a delta over L0, therefore it's just triggered this one. Otherwise L effective is still fine. As I mentioned, this is not the final ones, and these examples is. So let's calculate those values. So instead of L0, we're going to use L effective, we're going to use L0. K3, where is the K3? Go to the our beam to compliant clause 9.4.1. Let me write that. Clause 9.4.41. Let's get the K3. K3 equal to, let's read through it. So it's just below here. K3 is here. Oh, so just use clause 9.4.2 because rectangulars are supported on both edge on the four side. So let me change that clause. Clause 9.4.2. Just change this clause to here because we have rectangular slab. Yes, 7 meter by 5.5 meters supported. Yeah, it is supported on 4 edge, and in that case K3 equal to 1. So that's K3 equal to 1 because we have a rectangular slab and it's supported on the 4 edge. Now K4 value, the value of K4 shall be taken from this table 9.4.42. And now K4 value, that we're going to take from these tables. Does the questions mentions which one we need to design? um, Floors have always considered the support of this one, made of this one. No, it does not say. Now we need to make an engineer design decision. Design decision meaning that which one would be the control of our slab. So the panels which are at the corner would be the sensitive panel. They are the critical panel. So we're going to take this corner one, or this corner one are the design dominant. Design dominant meaning we're going to focus on this design. So for that case, I think Heather already discussed these. There are 9 different age conditions that standards wants you to talk about. Um, um, I also reviewed this American and all. They also have these 9 cases, American and European code. So I think you remember these diagrams. That's how you're going to read it. That okay, number 1, 4 ages are number 1, 4 ages are continuous. So this age continuous, this age continuous, this age continuous, this age continuous. So 4 ages are case number 1. Case number 2, 1 short age discontinuous. So you have long age continuous, short age continuous, 1 short age is discontinuous. So your slab is not continuing here, stop here. 1 long age discontinuous, number 3. So you have a short age, short age, but your 1 long age is discontinuous. 2 short age discontinuous, number 4. So you have a slab here, like you have balcony. You remember this kind of a balcony. If you have buildings, you have balcony, and your balcony is discontinuous in the short edge, and again continuous on here. You have some kind of support. So you have this case number 4. 2 long edge discontinuous, number 5. So you can see again balcony, but they are narrow and along this length is wide. So you have 2 this edge continuous and 2 edge are this 2 edge short edge are discontinuous, 2 long edge are discontinuous. Number 6, 2 adjacent edge discontinuous. Yes, adjacent edge meaning they are meeting each other and they are discontinuous. So number 6 is our critical panel. So this is the critical one. This one also critical. Number 7, 3 edge discontinuous. You have number 7. You have 1, 2, and 3 edge continuous. 1 edge is continuous. 3 edge discontinuous. Number 8. 3 edge discontinuous and 1 edge is continuous. And 4 edge discontinuous. These 4 of them are discontinuous. So I hope you understand how to read these tables. Similarly, this one appearing here as well. Now, as I mentioned, our panels is this one critical. Our panel is this one critical. So these has a case numbers. If you remember that case number 6 would be the case, because you have a corner panel, 2 adjacent edge are discontinuous, 2 adjacent edge are discontinuous. So case number 6 we're going to work through, that is case number 6. So let's say you have a age condition. We going to work through the clause again 9.4.42, and again we're going to work with table number 9.4.42, and in that one we have a age condition. Age conditions we going to age conditions that we're going to make it is 6. Age condition number 6. What is age condition 6? Meaning 2 adjacent ages discontinuous. Right, so that's all good. We have age condition 6 are discontinuous. Now Ly on Lx, I think we have calculated this Ly on Lx 1.4. If you remember that we done these calculations, Ly on Lx 1.4. Here you go, you have 1.4. So for that case we have everything. Meaning we're going to use this number 6, and we have 1.4. so we will be in here. We need to do the interpolation between these two numbers, 2.5, 2.25, and interpolations that can be done here. So let's do the interpolations. You have Ly on Lx value when is 1.25, your K4 value is 2.5. When your LYX 1.4, we need to calculate, and you have 2.25. No, the LY on LX is 1.5, and then you have 2.25. By the way, I just use these informations that your LY on LX 125, you have 2.5, LY on LX 1.5, you have 2.25, and we need to calculate for this 1.4. So we just take the ratio 1.5 take away 1.25 over respectively 2.25 take away 2.5 is equal to this 1.4 take away 1.25 over, let's put this as x or something, x take away 2.5. So if I just use the calculator, 1.5 take away 1.25 divided by 2.25 take away 2.5, you get -1 here. So 1.4 take away 1.25, x take away 2.5. So x take away 2.5, 1.4 take away 1.25 -1. So 1.4 take away 1.25 -1, you get -0.15, x equal to -0.15 plus 2.5, you get 2.35, and make sure it makes sense, right? 2.35, yes, it makes sense because it's between. As I mentioned, you always have a feeling that it should be number between this and this. 1.4 is close to this 1.5, so this number is close to 2.25. So 2.35 K4, we can take it K4 equal to 2.35. I hope you don't have any issue to. I think these are little bit different than one that we use in the one-way slabs, because we just need to consider these age conditions. Now K4 we done. Delta over LEF given to our example, which is 1 over 360, which is delta over L0. We convert that one, so we no need to worry about it. Thousands, EC is given in our examples. EC is given in our example 30,100. In case it's not given in our examples, for 32 megapascals given, in that case we can just borrow, or we can just read from the tables. That tables is here, table 3.1.2. for concrete compressed strength 32 megapascals, we can read from the table 30,100. Okay. So in that case we have this, in that case we have this 30,000 EC value, 30,100 megapascals. Now the last bit that we need to calculate is this effective load, effective design service load. That's the name written here, effective design service load, right? So let's put that effective design service load. Effective design service load, that is FD effective equal to. Now we have two different equations. You remember that we last times we used this equation KCSG SIS case 1 for deflection that occur after addition or attachment of the retail furnish or finish. I think we are just working with total deflections. So in that case we will have a total deflections. We have given the column that durability limit the total deflections. Here you go. They have saying that you need to use the total deflections. That is given here. Total deflections. So look, in the real world, in the graduates, when you work in the real situations, you can use this FD effective into the both cases. Like when you're designing in the real world, you need to do it both calculations, FD effective, and also you need to use the you need to use these both values A and B. You have FD effective using this one, and you can recalculate and get the B minimum using both values. Okay, but here in the example for theoretical purpose, it is given to us to use this one, so therefore we demonstrating this as this one, 1 plus KCS G plus short-term deflections, short-term deflection factors plus KCS, long-term deflections, and the live load, right? So that is the equation I just copied from that one. Now in KCS, which is the creep and shrinkage factors, that equations that we're going to take it from, I think, in the beam sections. I think we done it this one in the one-way slab too. We generally don't provide the compression reinforcement in the slab. Generally we will have only tensile reinforcement. We don't have. So KCS in the close 8.5.3.2, KCS equal to 2, take away 1.2, ASC on AST greater than or equal to 0.8. Now generally in the slab we don't provide the compression reinforcement, so compression reinforcement is 0. So 2 take away 0 is greater than 0.8 is just check is okay. So generally speaking, in all one-way slab or two-way slab, generally we have KCS equal to 2. The reason is we don't provide the compression reinforcement in the slab. So I can just copy that equations for the completeness of the examples. 2 take away 1.2 ASC on AST should be greater than or equal to 0.8, and that is coming from clause number 8.5.3.2. and for the slabs, if you have in the mid span, you have this AST here, and generally you have a top AST as well when you have at the support AST at the top, right? When you have a negative moments, we provide a tensile reinforcement here. When you have positive moments, you provide the bottom reinforcement, top reinforcement. Basically, when you have a slab like this, when it's bended, like you have negative, positive, and negative. So that is negative moment, and this is positive moment. So you provide the bottom reinforcement, and here you provide the top reinforcement or something like that. Okay, so ASC is always 0 in the slab. In that case, ASC equal to 0. We don't provide the compression reinforcement, so 2 take away 1.2 times 0 greater than or equal to 0. So 2 is the KCS value is 2, and we need to calculate. Look, this is the value. For that we need to use the trial slab depth, because this G is the dead load, right? So for that case, we need to calculate the dead load. G equal to density of the slab, kilonewton per meter cube times by the thickness of the slab. Therefore we need to use the trial thickness of the slab in the millimeters. So density given in our example 25 kilonewton per meter cube times by the thickness of the slab is the total thickness. That, by the way, we need to take it. Let me check it here. That 0.17, I think 170 millimeters that we where is the here we take it 170. Remember, ln over 29, so 170 millimeters. So you have a 0.17 meters. So this will give you 25 times 0.17. You get 40. What happens? Yep, sorry. 25 times 0.17, you get 4.25 as a dead load. Is the weight of the slab, by the way. This is kilopascal or kilonewton per meter square. So G would be the weight of the slab, plus there is a additional weight due to the partition due to the partition. There was 0.5 kilopascals given in our example. So we just need to add on the top of the weight of the slab, which is 4.25 and 0.5 kilopascals. So plus 0.5 kilopascals, you have 4.75 kilopascals. I hope you understand this. G live load is given 3 kilopascals. Office building, you remember that this is typical. When you have office buildings, you can close your eyes and just say that 3 kilopascals is the office buildings, and it's given in the example. So no problem. But if it's not given, you can use it from 1170.1. In case in the real situation you want to take it. So now we're going to use these equations to calculate that FD, effective service load, which is FD which is FD effective equal to 1 plus KCS G plus psi S plus KCS psi L times by the live load. So 1 plus KCS2 plus psi short term factor 0.7. I can show you where it's given. Long term factor 0.4, live load 3 kilopascals, and G we calculated 4.75 kilopascals. So 4.75 factors. Now short term factors and long term factors given in our examples. So we have a short term factors and long term factors given in our examples. So that is given. We can just calculate that. 1 plus 2 times by 4.75 plus 0.7 plus 2 times 0.4 times by 3, you get 18.75 kilopascals, right? And the units, you don't need to change it. Someone might say that let me play with the units. So the standards will going to tell you those units, saying that is in kilopascals, this one in megapascals. So someone might say this is not matching, kilopascal, megapascal, how come you are just putting kilopascal and megapascal? Look, they also already multiplied thousands and so on to take into account to kilonewton, and so they already done for us. So we no need to play with the unit for these cases, okay? Particularly for these equations, that we don't need to be consistent with the unit. Whatever they said here, we just take it as it is, okay? Okay, now we have all the parameters that we need to go for it, and we can calculate those L effective over D. So let's put this. I'm going to write this L effective instead of we're going to write LO, okay? Because in our examples is given in that fashion. I will write D minimum for our completeness or for our notations, okay? So I just change this one. In someone said, okay, this is quite confusing. Don't get confused. I also mentioned how you calculate L effective, okay? So it's not, if you take L0 still it's not an issue, okay? K3, K4, I'm just changing to delta L0 and 1000 EC on FD effective over 1/3. So L0, I think we calculated L0 somewhere. Let me go back all the way to L0 5150. Someone might say, what about other side? Like, why you're not taking this on other side? Because you have two L0. One is L0X and another one is L0Y. Now, when you do the trial depth, this is always short span. This is always short span. Always short span. Someone might say, why? How do I remember this short span? Look, when you have a slabs, you need to find it out who going to work hard. You have a short span and you have a long span. When you have long span, they will not be sensitive. Long span will have a higher moment. Sorry, short span has a higher moment. So you always have, this is a short span. So your design would be governed by the short span, like a one-way slab. Like this is the one-way slab. So this is a two-way slab, sorry, but you have two options. You can design it either for short span or long span. Who is a critical? Short span. You can imagine that, okay, if you have a span, who is going to work hard? That your short span would be working hard. So, okay, so I will show you how you can identify. But here we generally going to work for the short span. So you have 5150 millimeters D minimum less than or equal to, I think the each parameters we can calculate it. So let's extract those informations. K3 equal to 1. Let's read the K3 at the same time. K4 is 2.35. K3 equal to 1 and K4 was 2.35 unitless. Delta over L0, that is the deflection limit that is given, that our slab should not deflect that much, so is 1 over 360. So that is the 1 over 360 times by 1000 young modulus of the concrete given in our examples, and we also noted here 30,100. So that is 30,100 megapascals Don't play with the unit, as I mentioned. They done it for us. FD effective in the kilopascals, we just calculated 18.75 kilopascals and 1/3. Don't forget this 1/3. Okay, so 5150 millimeter over D minimum less than or equal to, let me work out this, 1 divided by 360 times by 1000 times by 3100 divided by 18.75 power 1 divided by 3 times by, I'm putting in my calculator. So you have this 38.68, and then you have, if I want to calculate the minimum, 5150 minimum over 38.68 less than or equal to the minimum. So 5150, you get about 133 millimeters about D minimum. Okay, so that is the D minimum. By the way, this is the D minimum, meaning this will give you this D minimum, this one. This is D minimum. Now if I want to calculate the overall depth, because you remember that we have 170 millimeters, right? That was our initial trial. If I want to calculate this minimum from the D minimum, then DS, overall depth of the minimum, equal to this D minimum plus this Rio. We are going to use N12 bars. Okay, we are going to use N12 bars. So that is plus 6 millimeters, because we need to add this 6 millimeter. And there was a cover 25 millimeters that is given to in our examples. So that is the 25 millimeters. So in that case, we have it 25 millimeters. 25 millimeters. So this D minimum that we're going to use is 133 millimeters. So if I just plus this one, 133 plus 6 plus 25, you get 164 millimeter. So I can say that D minimum should be greater than or equal to 133 millimeters, or DS overall minimum would be greater than or 164 millimeters. Now our assumption is DS equal to 170 millimeters. So we are okay, because DS 170 millimeters is greater than your DS minimum, which is 164 millimeters. Now you can continue your design using DS equal to 170 millimeters. That is no any issue. Okay, you can continue your design using DS equal to 170 millimeter, because it satisfies your serviceability conditions. So in that case, we can continue that DS equal to 170 millimeter. Now look, for real world, like when you work in the industry, your supervisors or who has a charter status, they might say, look guys, you 170 millimeters sounds good, it looks okay. Now we need to save some money. Meaning the standards has different values, standards has different methods, because you remember that for deflection calculations there are different methods. I can show it to you, those different methods, and different methods will give you different answers, because there are some assumptions that, okay, there are refined calculation, simplified calculations, and dim to comply. We use this one, and we found that is a 170 about that 153 millimeters. That's fine. Look, if you want to calculate more accurately, this is the more simplified calculation, would be the more accurate one. If you go through this one again, I am sure with the Excel calculator, Excel sheet, you might be able to reduce that depth to 150 millimeters. Okay, so we done the calculation in the background, so we know that this depth can be further reduced and they should be okay. So in case if you in your test or exams, if you continue doing 170 millimeters, that is okay. There is no any reduction of mark or anything. This is the understanding, 170 millimeters is okay. But for our case, we can optimization optimization, let's say that we can use DS equal to 150 millimeters, and we continue our design from there. In case if something goes wrong, we have an option to come back and use 170 millimeters, because as an engineer you need to do the look within the one try. You will not gonna get all these ones. In the ideal world, I'm showing you all this example, therefore it's working. but in ideal world you need to do some iterations. But here ds equal to 150 millimeters. I provide you the reasons, because this 170 millimeters coming from deemed to comply methods, and deemed to comply methods are conservative. Conservative meaning, yeah, they are safe. They are safe meaning they will be give you the thickness which is larger. But if you go to the simplified calculations which require more details calculations, take into account everything, in that case you are able to reduce that ds equal to ds value. So let's take 150 millimeters as a starting point and we optimize that, and I tell you the reason why that, right? Now our design is going to start now. After 1 hour of talking, we have not start our examples. What do you mean by not started our examples? We are just mingling about these trial depth and which one to start with and so on. But now we have a solid foundation that, okay, let's say ds minimum is 164 millimeters, ds 170 is okay. So we can just reduce a little bit and continue checking our examples. Now, so this is a starting point now. This, so far what we done is nothing, that we have this 150 ds value depth of the slabs that we're going to try everywhere. So this is, let's say, 150 millimeters, that the depth of the slabs we're going to try. Now, first of all, for that one, if you remember that we need to calculate a design action. Design action means what is the moment coming on to the slab. If you remember for one-way slab, you remember this one, closed 6.10.2 for one-way slab. I spent I think about half an hour or 15 minutes. I show you how you can calculate the positive and negative and shear force in the one-way slabs. If you remember that FD, LN, and so on, LN is the clear span, and FD is the dead load, 1.2 dead load plus 1.5 live load. That we done for one-way slab. Now for two-way slabs, that is here, that design moment is governed by this one here. I think you cannot see. I think there is. I just need to lower down this glass. Okay. All right, so I hope you can see more better now. Yeah, so here we have closed 6.10.3.2, which will allow us to calculate the positive bending moment, and there are negative design moments here as well. So this one here, it says that mx star, which is the x is, you remember that x is the shorter span. Shorter span moment, positive shorter span moment would be beta x, fd is 1.2g plus 1.5q, and lx square, and you already know lx, right? Lx is like a center to center distance. My square is equal to beta y fd lx. Look, this they have lx both side. Okay, don't be rushed and saying my equal to lx square. There is a theory behind it. I'm not sure whether look, I can show it to you, that theory as well. There is a theory behind it, that why we have only lx. Let me look. This theory is, if you don't understand, don't worry. It's not. I need to quickly run through it, that theory. Two-way slab theory, or where is it? This is, sorry, this is all my notes that I generally use it. Okay, that is here. So that theory is saying that, okay, this corner one is now this theory is saying that, okay, if you have a slab, two-way slabs, then the deflections in the middle, like deflection here in the middle, would be same, right? If you bend it about the red line or if you bend it about the blue line, but the deflection at the midpoint would be same. Do you agree with me that if you have a loading, then if you have a blue line 1 meter strip and the red line 1 meter strip, and if it is bended, if you take the beam along the red line, if you take the beam along the blue line, and if you're bending on the same loading, you will have same deflections. Everyone agree with me, right? So let's say you have a UDL load in the red line, then you remember that from our SD1 class 5 over 384 load over LX, this is LX over EI, that is the deflection here. And if you have QY, again you have 5 over 384 QY LY square over EI, that is the deflection at the midspan. And you know that deflection at that point is same on the LX side and all LY side. EI is cancelled on both sides. So you can able to just get the ratio, because your loading is Q equal to QX plus QY. Then in that case, you will be able to get these QX let me show you. You can be able to calculate this qx equal to q. Let me show you all the way from here. That this is a deflections, and then you can cancel this 50384. So qx lx to the power 4, qy l to the power 4, and then you can take qy is equal to lx on ly to the power 4 qx, or you can say qx is equal to ly on lx to the power 4 qy. So that is a relationship. The loading on the x directions would be power of 4 qy. Loading in the y direction is the power of 4 of this length ratio times qx. So if someone said that what side of the loading is more, you can see qx equal to load, because ly on lx would be greater than 1. The loading q equal to qx plus qy. So if you substitute this qx value like a qy value here, you will get as a terms of qx, and then you can say qx equal to q ly to the power 4. In that case, you can just know the UDL load moment is equal to qx lx square to the power 4. If you have this UDL load, the moment would be WL square over 8 if you have this W. So in that case, if you just plug the value qx and all, then you will say that these factors would be these factors here. These all the values would be your beta x, and that is your FD, let's say q lx square, and that is beta x. That's how they given in the tables. If you do it for y, let's say you want to get a qy and just do the all this one again you simplify that, you might end up with the lx square here, and then you have all these values here. That is your beta y, load FD lx square. That's how they get these values, that beta x FD lx square, beta y, and they also have a lx square. Okay, so that's just a quick theory behind it. So therefore they have just lx on the both sides. Okay, and this beta y, by the way, they calculated for us, so we no need to worry about this long theory. They have given to us here. So I hope you understand that. Let me go back to this table. So that's all good now. So let's calculate the moments. Let's calculate the positive moments. Let's calculate the mid span. At the mid span, you have positive moments. You have positive moments. At the mid span, you have positive moments. Let's say positive mx star equal to the equations that we're going to use is this one, because you have positive design moment along the x directions along the short span, beta x FD lx square. So that's fine. Beta x FD lx square. Now for that case, beta x, as you know, we are designing it for the condition number 6. I think we spent some time on condition number 6, and our ly on lx ratio is 1.4. so here you go, 1.4. so that is nicely suited here, 1.4, and condition 6 0.051. so beta x equal to 0.051. that is coming from table 6.10.3.2a, because age condition equal to 6 and ly on lx ratio equal to 1.4. FD value, FD equal to 1.2 G plus 1.5 Q. I think G we need to recalculate, because if you remember that we have a calculations for 170, but now we are using 1.5, sorry, 150. So you have 25 times 0.15, you get 3.75, and we need to add 0.5 extra, right? There is a partitions that is given in our example, so we just add 4.25 kilopascals. So FD equal to 1.2, dead load is 4.25 kilopascals, and live load is given to us is 3 kilopascals for office building. So let's say 1.2 times 4.25 plus 1.5 times 4 times 3, you get 9.6 kilopascals. So if I just calculate this positive bending moment in the x direction, shorter span, equal to beta x, we have 0.055 times by FD value is 9.6 kilopascals times by Lx square. I think the Lx we have it 5150. I think we calculate that one. Let's put 5.15 meters square. So if I just put that value in my calculator, times by 9.6 times by 5.15 square. So we will have a 0.055 times 9.6 times by 5.15 square. You get 14 kilonewton meters. Now we can stop here. Positive bending moment. I don't want to rush it to the last